All right, in 4.5, we're going to talk about the dimension of vector space, which is a word we've heard about and used quite a bit already, right? The word dimension. And the connotation and the meaning that comes along with the word dimension is actually aligns with what you think it does. But the interesting thing is it also aligns with some of the things we've learned about bases. Um, and so we're going to build up to that with this first theorem here. So this first theorem is telling us if we have a vector space with a specific basis b1 through bn, remember the definition of a basis means that the elements in here can be used to reconstruct any element in V. So they span the space is what that means. And these are also linearly independent. Um, so anyway, if we have a basis for that space, then if any set in V containing more than n vectors, right? So there's n vectors in this set. If we have more than that many vectors, it must be a linearly dependent set. Let me sort of describe to you the way that the proof of this would work. So this is going to be sort of just a quote-unquote proof. It's not going to be a hardcore rock-solid proof, but here's just sort of the idea. Well, let's say that this is a basis for V, right? So let's suppose we have a basis that has n elements, b1 to bn. And let's say that forms a basis for B. Then by definition, like I said, every element in V can be written as a linear combination of those things. So then every element in this vector space V can be written as a linear combination of these basis elements. These B1 through B, these are vectors. I forgot to put the vector sign on there. And so let's say we add another vector to this set. So let's call that Bn plus 1. So if we add Bn plus 1, so a new vector to the set, well, this B sub n plus 1, this new vector, is part of V because it's in the vector space, right? It's one of the elements. And so that means it can be written as a linear combination of the basis elements. Well, automatically that would make the set linearly dependent by definition, right? So as soon as we add this new element, if this is already a basis, b1 through bn, then adding this new one is in the span of those and it becomes linearly dependent. So if we add bn plus 1 to our basis beta, since our new vector bn plus 1 is in V, it can be written as a linear combination of the basis elements. And that, by definition, is linear dependence. So that would mean our new set would be n plus 1 in it is linearly dependent. And so this is sort of getting at the idea that, like, if we have a basis that has n elements, you couldn't possibly have a separate basis for the same space with n plus 1 elements, because as soon as you add another one, it becomes linearly dependent, which violates the definition of a basis. And so if we can, if the idea is like we need to have n elements in a specific basis for a specific space, then that means every basis in that space must also have n elements. So that leads, theorem line, this first theorem leads directly to theorem 10. If we have a vector space that has a basis with n vectors, then every basis for that space has to have exactly n vectors. And so, just to be clear, you can have more than one basis for the same space, but they need to have the same number of vectors. So just as a quick example here, the standard basis for R2 we know is 1, 0, 0, 1. So that has two elements, right? Well, another basis would be two other linearly independent vectors. So maybe it might be like 1, 2, -1, 4, for example. That would be a second basis for R2. It also has two elements, and so these are two different bases for R2, right? Different vectors, but they both have two elements. That's sort of the idea. So that's what theorem 10 is telling us. And so it actually turns out that the number of elements in the basis is called the dimension. And so that's what this definition, the next definition, tells us here. If V is spanned by a finite set, we say it's finite dimensional. And moreover, the dimension of the space V, written as dim V sometimes, dimension of V, is the number of vectors in a basis for V. And we just said all the bases have the same number of vectors, and so it doesn't matter which basis you look at, they're going to have the same number, and whatever number that is going to be the dimension. And so these two right here, for example, that we just wrote down, this is showing us that R2 is two-dimensional, and we would have guessed that. R2 is sort of like a flat piece of paper. A flat piece of paper, I think you would agree, is two-dimensional. Let's look at a couple other examples at the bottom here. So we've talked about R2. This is telling us the standard basis for Rn. So this is the standard basis for R2. The standard basis for Rn is the n vectors of the identity matrix for Rn. And so in R3, for example, if we wanted to think about the standard basis for R3, so not really in R3 because it's for R3, would be the R3 version of the one we just wrote down. So it would be 1, 0, 0, 0, 1, 0, 0, 0, 1. And we could say, well, there's three elements in there, and so R3 is three-dimensional. Three elements in the basis, and so that means that the dimension of R3 is 3. And, that should make sense. Like the physical world is R3, right? Or a box would be R3. And we know that we live in a three-dimensional world. So if I asked you, like, what dimension is the room you're in, you would probably say 3 dimensions. And so your intuition about the word dimension makes sense. What we're saying here, though, is it also just corresponds to the number of elements in the basis that you can use to generate that space. So with this in mind, this has 2 elements, and so this means the dimension of R2 is 2, right? Dimension of R3 is 3. What do you think, in general, the dimension of Rn is? So the dimension of Rn is n, for whatever n you choose. Right? Dimension of R4 is 4. Dimension of R3 is 3. Dimension of R10 would be 10. Okay, so those are a couple bases and examples in Rn, and again, it makes the dimension in Rn kind of makes intuitive sense to what you would probably think if I just asked you without teaching you this first. And so let's look at an abstract vector space in this case. So let's look at P2, and I'll remind you, P2 means polynomials of degree 2. And so, a general second degree polynomial would look like at squared plus bt plus c, where a, b, and c are constants. Well, we've seen the standard basis for polynomials in general, and polynomials of degree 2 would be linear combinations of t squared, t, and the number 1. And so the standard basis for P2 is 1, t, and t squared. Right? You can build any degree 2 polynomial by doing linear combinations of those 3 things. And so that obviously has 3 elements. And so this means the dimension of P2 is 3. If we were talking about P3, we would add a t cubed term, right? Because that would be degree 3. If we were talking about P4, we'd add 2 more terms, a cube and a 4th term. And so with that in mind, take a second and think about what is the dimension of Pn. And so that would be n degree polynomials. Well, you're always going to need n plus 1 elements in your basis because you need 1 for every power, and then you need the constant term, right? So for example, if you want to make a squared polynomial like this one, you need the square term, the t term, and the constant. And so you need 3 elements to make a degree 2, right? You'll need 4 elements to make a degree 3. You'll need 5 elements to make a degree 5, 6, etc. 4, excuse me. You need 1 more basis element than you need the dimension of. Okay. So let's take a look and relate it back to some things we've seen in past sections, and also get a visual representation of what we're talking about, sort of an additional visual representation here. So we saw problems like this in the basis section, maybe. I think that we saw problems where H is basically defined as a subspace of, in this case, a subspace of R4, where we're specifically sort of specifying what the components need to be. Right? So it's 4-dimensional, but we're sort of specifying each entry in some way. And so let's find the dimension of this subspace defined by this. In order to do that, we need a basis. So we'll need to figure out a basis for this space H in order to figure out the dimension, right? Because the dimension is just the number of basis elements. So let's figure out a basis. Well, you remember how this one works, is we can break this thing up into the different components, A and B. So in other words, H equals the thing we're given. I'm just going to rewrite it here. And then let's break it up into the A, B components. So it would be A, 2A, 3A, 0, plus B, 0, minus B, minus B. All right, so I'm breaking it up into the A's and the B's, and then let's factor the A and the B out. And so it's A times 1, 2, 3, 0, plus B times 1, 0, minus 1, minus 1. And so what we're really doing, what H really is, which is this original vector, it's really the span of these two vectors, right? We're doing linear combinations of those two vectors. Right, so let's write that down. So that is all elements in this vector space H, the subspace, are linear combinations of those two vectors, 1, 2, 3, 0, and 1, 0, minus 1, minus 1. And these things are linearly independent. We can just look and see they're linearly independent because you can't multiply one of them by a constant to get the other one. The other way to see that is if we row reduce the matrix, the homogeneous equation, there'd be a pivot in each column, which means there's no free variables, right? And so, in other words, those two vectors form a basis for this space. So H has basis beta equals those two vectors. And this thing has 2 elements in it, and so the dimension of the space is 2. Right, so this basis has 2 elements, and we just saw on the last page that the dimension of the space is the number of elements in the basis. So the dimension of H in this case is 2. And so, practically speaking, what that means is the space defined by this vector is a 2-dimensional subspace of R4. Right? So we're in R4 because these vectors have 4 elements in them, right? 4 entries, I should say. But there's only two vectors in the basis. And so whatever sort of space this H space makes, it's 2-dimensional. And so it's like a piece of paper, which is 2-dimensional, cutting through R4. Now we can't visualize R4, but it'd be sort of like this piece of paper right here, right? So this picture, I mean. So this picture right here, the box would be R3, and then the piece of paper that's inside it that's highlighted right here would be a 2-dimensional subset of that 3-dimensional space. And so that's sort of the idea with this one, except we're in R4 instead of R3. And so let me just sort of drive home that with these visual representations. These are specific visual representations of dimensions of subspaces of R3 specifically. And we're talking about R3 because we're looking at the boxes here, and we have X1, X2, X3 on each one of those boxes. And so the first thing we're being shown is that a single point, which is what's being shown at the origin right here, is zero-dimensional. So a single point would be zero-dimensional because you can't even do a span of something to get a single point. It's just a point. But a line in the space is one-dimensional. So if this thing is like, let's call this vector v1. If you did the span of that vector, it would be this entire line. Right, so that we talked about this in the span section in chapter 1. And so what the reason for that is, I think you would agree that a line is one-dimensional, just kind of practically speaking. And the reason it's one-dimensional from a mathematical standpoint is because it's the span of a single vector. In other words, there's a single vector in the basis. Right, so lines are one-dimensional because their bases consist of a single vector. So we're kind of throwing it back to that early section about spanning. The other thing we learned in that spanning section, as soon as we add a second vector, so here's my v1, here's v2, when we do the span of two vectors, it creates an entire plane. And so the entire plane would be the span of v1, v2. Again, go back to the span section to remind yourself of that. And so that's what's being shown inside this space. This two-dimensional object, this plane inside here, which you could think of again as like a piece of paper floating through a box, is two-dimensional because there might be two vectors that you can use to create that plane, very similar to that picture. And then, once you add a third vector, you would create the box, which would be three-dimensional. So this is showing us that the box here is a three-dimensional object, and in order to create that box, we would need three elements in the basis. And so I just want to add that note. So all planes are 2D because those planes are spanned by two vectors, linearly independent vectors. In other words, the basis has two elements. And the interesting thing is, like in this picture, this piece of paper would be a two-dimensional subset, or subspace in this case, of R3. So R3 would be the bigger object, but these vectors would still be in R3, right? So you'd need three entries to build each one of those, but there's only two of them. So in this particular picture right here, we have a 2D subspace of R3, right? A two-dimensional subspace of a three-dimensional object, which is R3. So I hope that kind of gives you the idea about dimensions and sort of links your intuitive thought about what dimensions are to the concept of bases. And now we're just going to basically apply it in a couple ways and think about sort of the general idea here. And so Theorem 11 should, if you know what I just said here makes sense, then Theorem 11 should follow very straightforwardly. So Theorem 11 is telling us if H is a subspace of a larger vector space V, so think about like this piece of paper inside the box, so to speak, then any linearly independent set in H can be expanded, if necessary, to a basis. So it's like, if we have a linearly independent set, if it's not enough to form a basis, we can add a few things to make it a basis. And moreover, dimensions of the inner space has to be less than or equal to the dimension of the outer space. Again, right, you can have a two-dimensional space inside a three-dimensional space, but you can't have a three-dimensional space inside of a two-dimensional space is sort of what this is trying to sell us right here. And so that should make some sense. And the equality would be if the two things were the same space. And then the second theorem is also sort of kind of follow similarly. So let V be p-dimensional vector space, so it's finite dimensional. Any linearly independent set of vectors in that space, of p elements that is automatically a basis. And so it's saying if we're p-dimensional, we know we have p elements in the vector space, and so if we have p elements and they're linearly independent, then it automatically satisfies the things that are required to be a basis. So these two theorems here are just two extensions of previous ideas. Not huge big deals, but hopefully they make sense sort of if you've been following along and the idea of a dimension makes sense to you. Okay, so let's look at some specific types of dimension and relate it back to null space and column space here. So that's the next topic, the dimension of the null space and the dimension of the column space. Right, so I'll remind you, null A means null space of matrix A, col A means the column space. And these two definitions that are at the top of the page were in section 4.2. And so I'm just rewriting them here to remind you about what those two things are. If you want more details, you might want to look at 4.2. Let me just remind you real quick. So the null space of a specific matrix is the collection of all x's that when you multiply it by the matrix, you get sent to the 0 vector, right? And so you might want to just add that down here if you're not clear about what the null space is. The null space is the vectors that are sent to 0 by A, right? So like AX equals 0. So the vectors X that get sent to 0. And then the column space, like it says here, if A is a collection of columns, then the column space is just the span of all those columns. Right? And so the column space, if you don't remember this from 4.2, it's all linear combinations of the columns. And we talked about how to find bases for both of these in the basis section. And I'll just remind you that when you find a basis for either one, it involves row reducing A, right? And so if we want to find a basis for either of these spaces, we row reduce A, just like we always do. We always row reduce. And this leads to the following definition. So this following definition follows directly from this concept. It turns out that the dimension of the null space, so the number of basis elements in the null space, is the number of free variables, right? And it turns out that the dimension of the column space is the number of pivots. And so it's very easy to figure out, and when you add both of those things together, you get the total number of columns, right? And so if you have a matrix, you just row reduce it, and you look for the pivots and the free variables, and those tell you the dimension of the null space and the column space. And so, let's find the null A and column A for this, and I should have said, let's find the dimension of them. It's missing the word dimension. So let's find the dimension of the null space and the column space for these two things. And so notice that this is already reduced, right? So this is already in row echelon form. It's not fully reduced, but it is in REF, and we are able to look at pivots and free variables in this form, right? Because we got a pivot here, down right pivot here, down right pivot there, and so we're able to see the pivots. And so let's label the pivots with a P, and let's label the free variables with an F. And so we've got a pivot column here, a pivot column here, and a pivot column here. And that means the rest are free. And so the number of pivot columns tells us the dimension of the column space, and the number of free variables tells us the dimension of the null space, right? Because for the null space, we solve AX equal to 0, which means we look for the free variables. And for the column space, if you remember, what we do is we look for the pivot columns. And so, so based on this, null space of A has 3 elements in the basis. Oops, basis, because there's 3 free variables. And we also see that the column space of A has 3 elements in the basis. because it has 3 pivots. And so based on both those things, we can see that the dimension of the null space is 3. Right? It's the number of free variables. And the dimension, this tells us the dimension of the column space is also 3. It just so happens to be the same, but that's just because the number of pivots happen to work out the same as the number of free. And it turns out the number of pivots is a term in itself, which is actually the focus, or one of the focuses of the next section. And so I'll just mention that here. We call the dimension of the column space, which is the number of pivots, the rank of matrix A. And this is what the next section's all about. And so I'm actually going to go right into that section since it's directly related to this. And a fairly short section. And so let's jump right into that next section by looking at the first page. And you can see that word rank is right at the top, the thing I just sort of ended the last section with. And it's defined very quickly, right? So the rank of a matrix is a pretty important metric, especially when you get into advanced classes. And like it says, the rank is the dimension of the column space of A. And what we just said on the last page, in the last section, another way to rephrase this is that it's the number of elements in the basis for the column space. Which we also said was the number of pivots, number of pivot columns, right? Hopefully you're kind of seeing by this point in the course that like so many things in linear algebra are just tied together, and you can say the same thing a million different ways. That's what the inverse matrix theorem is all about, really just tying all those different things together. And so with that in mind, this theorem maybe some of you are already thinking about this theorem, really. And so let's see what this says. So the dimensions of the column space and the row space of an m by n matrix, so not necessarily square, are equal. And moreover, the common dimension, which we call the rank, also equals the number of pivot positions, which we just said, and satisfies this equation, right? And so first of all, well, let's sort of rewrite this, right? So rank of A, what this equation is saying. So it's saying the rank of the matrix plus the dimension of the null space equals n. And the rank is the dimension of the column space. So the dimension of the column space plus the dimension of the null space equals n. In other words, like this, once we rephrase this, hopefully this will make sense. That is, and n, let me sort of first say this, n is the number of columns. Right, so n is the number of columns. And so when we say rank plus dimension of the null space equals n, what we're saying is rank, which is the number of pivots, columns, plus the dimension of the null space, which is the number of free variables. And when you have a matrix, a column is either a pivot or a free variable, right? There's no other option. And so if you take the number of pivot columns plus the number of free variables, those are the only options, and so that should be the total number of columns. And so that's what this theorem is telling us. It's telling us when we add the number of pivots plus the number of free variables, we get the total number of columns. And we think about these things a little bit differently. I know, like the dimension of the null space, that's how many basis elements are in the space that gets sent to 0. And I know pivot columns talks about sort of the rank and the number of basis elements in the column space. But really, we're just adding up the column numbers and getting the total number. The type of problems that this comes up in is if a couple pieces of those information, you can figure out the other piece is sort of one of the ways these things come up. And then it also has a really direct application to the invertible matrix theorem as well. So let's look at a couple straightforward examples first on the bottom here. So this first one's telling us the null space of a 7x6 matrix A is 5-dimensional. What's the dimension of the column space? Well, if we have a 7x6 matrix, that means there's 6 columns, right? And so this is the first thing we should note A has 6 columns. And so this is telling us n is 6 in the above equation here, right? N is 6. We're being told right away that the dimension of the null space is 5. And so dim null A is 5. And so we know 2 pieces of information in this equation, right? We know the dimension of the null space, we know n, and the question is, what's the dimension of the column space, which is the rank? And so we know that rank plus dimension of the null space equals n, and we know 2 of those things. And so really we know that rank plus 5 equals 6, and so that means the rank is 1, right? So then that means the rank of A is 1, which is also known as the dimension of the column space. So sort of simple-ish problems that are like these are, it gives you like gives you 2 pieces of information in this equation. You need to figure out where they go, and then you find the third piece. Very, very common answer, or common problem. Okay, another sort of similar problem looks like this. So let's say we have a 5 by 6 matrix. So let's say we have a 5 by 6 matrix, and it has 4 pivot columns. What's the dimension of the null space? And then the second part of this is, does the column space equal R4? Okay, so let's just the first part of the question doesn't take very much. So draw a line down the middle of the page here, because we're going to answer both parts of the question here. So if we have a 5 by 6 matrix, this is telling us that n is 6 in the above equation, right? And then we're being told that there's 4 pivot columns, and so that tells us that the rank is 4, which is the dimension of the column space. And so we're given 2 of those things, so we can figure out the null space then, right? So then we have 4 plus the dimension of the null space equals 6, and so that means the dimension of the null space is 2. The second part of the question is the more interesting one now. So does the column space equal R4? So we're being told that like it has 4 pivot columns, which means that the rank of A is 4. And so we're being told the dimension of the column space is 4. But does that mean that the column space equals R4? Just because it's 4-dimensional, is it R4? Well, let's just take a look at this picture on the last page. 2 pages ago, excuse me, from the last section. Right, this was a picture of a 2-dimensional object, a piece of paper, going through 3-dimensional space. And so this is a 2-dimensional subset of R3, but it's not necessarily R2. Right? R2 is a completely different space that only has 2 entries, and the entries that are in this piece of paper right here have 3 entries. And so just because something is 4-dimensional in this case doesn't mean it is R4. Right? Because things in this space are actually size 5. And so we have a 4-dimensional subspace of R5. So let me write that down, and then I'll try to reiterate it. This is a kind of an important conceptual thing that I think is kind of interesting and cool. I always feel like we're on talking about Star Trek or I don't know, some outer space thing, when we're talking about different dimensions and things like that. If we can understand this, it really brings meaning to some of this linear algebra. So the idea here is A is a 5 by 6, right? And so if you wanted to multiply something by A, it has to be 5 by 1. And things in the null space, you multiply by A. And so A is 5 by 6, so that means elements in the column space are going to be 5 by 1. Right, because let me just be more clear about that. If you wanted to do A times X and get 0, you're doing a 5 by 6. I'm sorry, I was confusing null space and column space. So if A is a 5 by 6, sorry, I got confused there for a second. We're talking about the column space. if A is a 5 by 6, that means A is a bunch of 5 by 1 vectors. Right? A bunch of 5 by 1 columns. 6 of them. And so each element in the column space is a 5 by 1, is what I meant to say here, right? And so when we say that the column space has 4 dimensions, it's 4 basis elements that are each 5 by 1. And so each thing is 5 by 1, i.e., each column is in R5. And so when we say that the column space equals dimension 4, what that means is that the column space is a 4-dimensional subspace of R5. I guess we don't know it's a subspace, so it's at least a subset, right? If it's a subspace, it needs to satisfy the subspace properties, and we're not being careful enough to assume that it does necessarily. So let's just call it a subset. It might be a subspace, but let's not be too careful about that right now. Right, but the point is, having dimension 4 doesn't mean it's R4. It just means it's 4-dimensional. And so we have a 4-dimensional subset of R5 in this case. Okay. The last thing we just want to relate this to, this section 2, is the invertible matrix theorem. And so we're actually able to tack on a number of additions to the invertible matrix theorem using the concept of rank here. And so we're going to kind of round that out in chapter 4 here with the following concept. So let's look at this example, which will motivate the theorem at the bottom, which is just adding some stuff to the IMT. Okay, so let's say that a system of 6 linear equations with 8 unknowns has 2 free variables. Is it possible the same system of equations will ever produce an inconsistent matrix in reduced form? All right, let's figure this out. So A, we're being told, if we made this into a matrix, it would be 6 equations, so it would have 6 rows, and 8 unknowns, so 8 columns. And so we're being told A is a 6 by 8 matrix. And so that means when you multiply it by a vector, it becomes a 6 by 1. And so when you multiply A by X, the solutions are 6 by 1. In other words, they're in R6. Sorry, I didn't realize I was off screen. Hope you can see that. Right, so 6 equations and 8 unknowns means we have a 6 by 8 matrix. And that means when we do A times some vector, it produces a 6 by 1. We're being told we have 2 free variables. And so if there's 2 free variables, that tells us about the null space. So 2 free variables means that the dimension of our null space is 2. And we know that the n is 8, and so we know that 2 plus rank equals 8, right? Because 8 comes from this right here. And so based on this, our rank is 6. Okay, so we have enough to answer this. I want to make sure everyone's sort of caught up here, and I would maybe just pause the video real quick and make sure that this makes sense. Let me reiterate quick. We've got a 6 by 8 matrix. Solutions to this are 6 by 1. And then we use the theorem on the last page, this rank plus dimension equals n, to figure out that the rank of this thing is 6. And so that's helpful because this means that when we row reduce the matrix, it's going to have a pivot in 6 rows, right? In other words, the column space spans a six-dimensional subset of R6. And so, since the solutions of AX are 6 by 1, since there's going to be a pivot in 6 rows, we're going to span a six-dimensional space. And so, is it possible for the same system of equations to produce an inconsistent matrix? The answer is no, because we just said the columns span a six-dimensional space, and so it's like a six-dimensional subset of R6, so it has to be the whole space. So that's sort of the setup. Let me see if I can write some of that down and make sense of it. So the first thing that we note that is like, since the dimension of the column space is 6, which is the rank, right? The rank is the dimension of the column space. That means the columns span a six-dimensional subset of R6. Okay, so in other words, it fills up the whole space. Right? A three-dimensional subset of R3 would be R3. A two-dimensional subset of R2 is R2. And so a six-dimensional subset of R6 is R6. And so in other words, the other way to say this, that is, the columns span all of R6. And what that means practically is every element in R6, that says elements, every element in R6 are a linear combination of the columns. Right, the columns span a six-dimensional subspace of R6, so that means everything in R6 can be written as a span, some linear combination of those columns. And so if we're thinking about AX equals B in this solution like we were doing before, the B's are 6 by 1. Right, so B is a 6 by 1. And so that means if we row reduced AX equals B, it's always going to be consistent because we'll have a pivot in 6 columns. And so AX equal B will always have a solution. And so if it always has a solution, the matrix is never inconsistent. So you can, again, kind of see how all these things tie together in linear algebra. We can kind of say, well, this leads to this, and if this leads to this, and this leads to this, and they all sort of mean the same thing, but tying them together in this kind of way really shows our understanding and shows the power and the sort of the beauty in a lot of ways of linear algebra. And so with that in mind, you know, I hope this problem sort of sees how some of the things like rank and dimension of column space relate to things like being consistent and spanning the space and having solutions and having a certain number of pivots. And so the final thing to sort of note here is we can add a bunch of things to the invertible matrix theorem. Right? So the concept presented in the above example leads directly to the additions to the IMT. And so the last place we left off was at letter L, and so you can see we're picking up at M, N, O, P, Q, R, and so we've tacked on 6 more things. And so it turns out these things are equivalent to a matrix being invertible. The columns forming a basis for Rn, the column space being Rn, so those two things, M and N, are literally saying the same thing, and so is O, right? The dimension of the column space being N. So M, N, and O are just restating the same thing 3 times, and P, Q, and R are restating the same thing 3 times. I'm sorry, P is actually another way of saying M, N, O, and P are all the same, right? So the rank is the same thing as the dimension of the column space. If they're both N, that means that the column space spans Rn, which means if it spans Rn, you can form a basis for Rn, right? And then Q and O are the same thing, right? So the dimension of the null space being the 0 vector is the same thing as, the dimension of the null space being 0 is the same thing as the null space just being the homogeneous, the trivial solution, the 0 vector itself. And so you'll kind of notice that each one of these things, the way you would test for each one of these things is by row reducing a matrix, right? And all of these things correspond to n pivots and no free variables. So all parts above imply the matrix A, and we're talking about a square matrix, remember, has n pivots and no free variables. The flip side of that is, well, if we have a free variable, that means we're not going to span Rn, and if we don't span Rn, there's less than one n pivots, and that means A is not invertible, right? And so the flip side would be like, if we have a free variable, the columns won't span Rn anymore, and so the whole IMT fails. In particular, there would be less than n pivots, and the matrix A would be non-invertible or singular. And so 6 more things to tack onto the invertible matrix theorem. Yes, the invertible matrix theorem is something you should really know for tests and the final specifically. I'm going to ask some sort of invertible matrix theorem questions where I give you one piece of information in the matrix theorem and ask you what the implications are for the other one. You're certainly welcome to sit down and memorize, A through R parts, but as I've tried to sort of encourage you in the way I sort of try to explain these things is if it just makes sense, you don't have to do as much memorization, because if it makes sense, you can just reason through problems like these. And so I would really encourage you to think about it from that perspective. Okay, thank you for listening.